Stephen William Hawking was an English theoretical physicist, cosmologist, and author, who was Director of Research at the Centre for Theoretical Cosmology at the University of Cambridge at the time of his passing. Hawking's scientific contributions included a collaboration with Roger Penrose on gravitational singularity theorems, within the framework of general relativity, and the theoretical prediction that black holes emit radiation, which is commonly referred to as Hawking radiation. Welcome back to my channel. Thomas Hertog, a key collaborator of Stephen Hawking, proposed an interesting approach on what could have been the last thoughts of Professor Hawking on the origin of the universe. In the late 1970s, after the publication of additional research, the discovery was widely regarded as a significant breakthrough in theoretical physics. Hawking was the first to propose a cosmology theory based on the combination of general relativity and quantum mechanics. He was an ardent supporter of the interpretation of quantum mechanics as having multiple universes. Hawking and Hertog addressed the problem of cosmic inflation, a colossal growth that allegedly elongated the neonate universe within the first moments. Inflation, which was conceived in 1979 by American theorist Alan Guth, holds that shortly after the Big Bang, space expanded exponentially, before slowing markedly. The inflation theory predicts with extreme precision that the universe should be flat. Dark energy is required to flatten the universe's overall curvature beyond the capabilities of ordinary matter and dark matter. This dark energy is likely the vacuum energy, also known as the cosmological constant. Clearly, the universe is filled with galaxies everywhere you look, and at the most largest scales, the universe appears to be flat, isotropic and homogeneous. Inflation, according to the theory, enlarged the initially infinitesimal quantum fluctuations to extragalactic proportions, but more on inflation theory in a dedicated episode in the next weeks. Studies of the CMB and galaxies strikingly affirm this distribution. Here is where the concept of inflation encounters its own problems. Physicists don't like the notion that inflation would abruptly cease for no apparent reason. They would prefer a mechanism that explains the causes of inflation and its cessation. As a result, they hypothesized that a quantum field drove it before it ceased to exist. The Professor Hertog theory proposes that the field begins in a false vacuum state of elevated energy and instability, in which space expands exponentially. The universe then returns to its true state of lowest energy, where space expands much more slowly. However, the scenario works a little too well. The exponentially expanding illusory vacuum produces more and more of itself, resulting in the expansion of space at an astoundingly rapid rate. Our universe is a region that has transitioned into a state of low-energy true vacuum. Such transitions should occur randomly, so there should be an abundance of other universes. In fact, the process should result in an ever-increasing quantity of space expanding at an exponential rate, with an infinite number of pocket universes expanding at a slower rate. But this is debatable among physicists. Depending on who you ask, you will find adepts to the theory, or other against it. However, the work of Hawking and Hertog have its own merit. Existence of all these other universes would not affect our universe on the most fundamental level. They are simply disconnected to have any relationship with ours. The concept of eternal inflation and a multiverse may undermine cosmologists' efforts to explain why the universe is the way it is. Things such as the values of essential physical constants could vary arbitrarily between pocket universes, rendering irrelevant any attempt to explain why they have the values they do in our universe. It can be determined by random chance, which is not very satisfying. Hawking contends that eternal inflation does not exist. Several of Hawking's popular science works, in which he discussed his theories and cosmology in general, were commercially successful. A Brief History of Time was on the Sunday Times bestseller list for a record-setting 237 weeks. A Brief History of Time, published in 1988, introduced the world to the views of a theoretical physicist on cosmology. Less known is the fact that Hawking continued to refine his theories on cosmic evolution until his death in 2018. Belgian cosmologist and professor, Thomas Hertog, a key collaborator of Stephen Hawking, in his latest book, On the Origin of Time, Stephen Hawking's Final Theory, proposes a compelling in-depth re-examination on Hawking's final views on the origin of our universe. Eternal inflation emerges because in the very early universe, the quantum fluctuations in the field that drives inflation are as big as the field's average value. But Hawking and Hertog argue that under those conditions one cannot simply carry on with Albert Einstein's general theory of relativity, but instead must use a maneuver like Maldaceni's to view the entire situation in a space with one less dimension. In that alternative space, things are more tractable, and the physics does not lead to eternal inflation. Instead, a single, well-behaved universe emerges. Hawking contends that eternal inflation does not exist. To put it in context, in order to accomplish this they borrow a concept from string theory that allows them to compare two distinct types of theories with distinct dimensions. In 1997, Juan Maldacena, an Argentine-American theorist, pondered a volume of space in which gravity was at work. Maldacena demonstrated that the theory was equivalent to a quantum theory on the space's boundary that did not include gravity, a conformal field theory with one less dimension that describe everything that it happens in the bulk, which is a space with one more spatial dimension. In that space, gravity exists and is fully describable on the boundary within this context. The space Juan Maldacena is so elegantly described is called anti-de Sitter space, and although is not the kind of space that describes our universe, the work has a tremendous importance since seems to be the key to unlock the theory of quantum gravity. In the early 1980s, numerous cosmologists were captivated by the concept of a multiverse, which is a fictitious collection of an apparently infinite number of universes. However, Hawking was evidently unsatisfied with these multiverse theories. And towards the end of his life, he sought a theory of cosmogenesis that addresses some of the most fundamental philosophical questions regarding the evolution of a universe capable of sustaining stars, galaxies, and intelligent life. Maldacena equated one theory to another in a space with one fewer spatial dimension in his work. And according to Professor Hertog, the principle of holography permits theorists to abandon the time dimension. Consequently, according to Hawking and Hertog's theory, the very early universe should be described by a theory with only three spatial dimensions and no time. Since it became evident that the universe had a beginning, the instant of its creation has been a source of consternation for theorists. Einstein's general theory of relativity does a good job of explaining events after the Big Bang, but it cannot account for the moment of creation itself. This instant creates a singularity in space-time, analogous to an infinitely expanding mathematical function, which undermines the theory. Therefore, theorists have for a long time sought a means to avoid this singularity, and losing time would be one method. When we trace the history of the universe back to its inception, we encounter a deeper level of evolution in which the physical laws themselves change. In the primordial universe, the laws of physics undergo a process of stochastic variation and selection, analogous to Darwinian evolution, with particle species, forces, and even time dissipating into the Big Bang. Gravity is a fundamentally exceedingly weak force. If it were stronger, stars would radiate more brightly and therefore die much sooner, leaving no time for complex life to evolve. If temperature differences in the CMB radiation were even 1 part in 10,000 times greater, most of the seeds of cosmic structures would have grown into monstrous black holes rather than hospitable galaxies with abundant stars. Adding a single space dimension renders atoms and planetary orbits unstable. As a result, the Earth would spiral into the Sun instead of following a stable orbit around it. Carbon is essential for all known forms of existence. And the efficient synthesis of carbon, from helium atoms within stars, depends on a delicate equilibrium between the cosmos' strong nuclear force and the electromagnetic force. If the strong force was a fraction stronger or weaker, the nuclear binding energies would shift, jeopardizing the fusion of carbon and, consequently, the emergence of carbon-based life. In 1981, Stephen Hawking proposed a universe without boundaries and a possible beginning. And despite a slight retreat, he never truly embraced the concept of a multiverse. Nevertheless, he acknowledged that the universe underwent a rapid expansion that cosmologists refer to as inflation, the post-Big Bang exponential expansion of spacetime. What fueled this massive expansion in the first trillionths of a second after the Big Bang is still unknown. Today, years after the death of Stephen Hawking, we still have no answers. However, there is optimism that ground-based gravity wave astronomers will have detected inflationary gravitational radiation within the next decade. This may provide astrophysicists with a new perspective on Big Bang cosmology. Professor Hertog claims that Hawking's entire career was captivated by this problem. Thank you for watching.